Hello, this is the fourth video of a preliminary series on sets, permutations and combinations for OCR AS Discrete Further Maths. This video is an introduction to permutations and the way in which they may be used to solve problems. Consider three people, Ray, Sanjay and Toni, known as R, S and T, joining a queue. In how many different ways or orders might they do this, if it does matter who goes first? Where order matters, we call these permutations or arrangements. A small problem, one way to find the solution is to list the options. We could have Ray going first, and then Sanjay and Toni. Or we could still have R at the front, and then T and S. STR or SRT. TRS or TSR. We can see here there are 6 ways. So for that first person in the queue, we had 3 choices. And then for the second slot, we only had 2 choices. And then for the third, there was only 1 choice. Altogether, as you can see by listing, there were 6 ways. So, having worked out there are 6 different permutations of 3 objects, how many different permutations can we make with 4 objects? We need a systematic and scalable approach so that we don't have to rely on listing, which is often impractical. If, as we did before, we looked at the many ways we could fill the slots with 4 objects, then we could argue that there are 4 choices from the 4 objects for the first slot. One of those now being taken, there are only 3 choices for the next, 2 for the third slot, and only 1 choice left for the fourth slot. If we multiply those together, we would get a number we call 4 factorial, or 4 times 6. So in other words, we had 4 choices for the first slot, and then we had the same situation as we did for the 3 people in the queue. 4 6s are 24. You could probably also find the factorial button on your calculator. For 5, the first slot then would have 5 choices, so we would have 5 times 4 factorial, in other words 5 factorial, and for n, n factorial. Another notation you might see is given in this red box here. Let's have a think about permutations with repetition. How many different arrangements can be made using all of the letters from the word happy, where there are 5 letters but one of the letters is repeated twice, and bananas, where there are 7 letters but one letter A is repeated 3 times and the letter N repeated twice? Well, there are 5 factorial arrangements of the 5 objects or 5 letters in the word happy, but not all will be distinct or different since we can't tell the difference between the 2 P's. For instance, HAP1P2Y is the same as HAP2P1Y. Therefore, those objects P1, P2, which would have 2 factorial ways of arranging them, will not be counted, so we need to divide the 5 factorial by that 2 factorial. Similarly, for the word bananas, there are 7 letters, but instead of there being a total of 7 factorial permutations, we need to divide by 2 factorial to account for the 2 n's, and by 3 factorial to account for the 3 a's, which will not be distinguishable. Therefore, in terms of the total permutations, for the word happy, we would have 5 factorial divided by 2 factorial, giving 60. And for the word bananas, 7 factorial divided by 3 factorial, and also divided by 2 factorial, giving 420 different permutations. If we are to look at permutations of subsets, then an example of this is to consider how many different 5-digit numbers can be made out of the digits 1 to 9 inclusive, if no digit is allowed to be used more than once. Notice we are only using 5 of the objects, a subset of the 9 objects. Let's have a think about this then. So we have 9 choices for that first slot. Having used 1, we only have 8 choices for the next, because no digit is allowed to be used more than once. And then 7, and then 6, and then 5. So a little bit of reasoning has shown us that that would give us the total number of permutations. But there is another way to look at this. It can be generalized by considering that if you divided 9 factorial by 9 minus 5 factorial, we would get the same number. This is the number of permutations of 5 objects chosen from 9 distinct objects. To generalize, we want to know how many permutations there are of R objects chosen from N distinct objects. As you can see here, instead of a 9 we have N, and instead of 5 we have R. This gives us N factorial over N minus R factorial. You may see this written as a formula using this notation. NPR will be a button on your calculator, and it will give you the N factorial over N minus R factorial calculation. In contrast, let us look at the issue that we could use the digits more than once. So if we have 9 digits and we want to make different 5-digit numbers, we will have 9 options for the first slot and still 9 options for the second, third, 4th and 5th. This would give us 9 to the 5, which actually is a much bigger number than the 9 factorial over 4 factorial, being 59049 compared to the 15120 that we would get in terms of a number of permutations if we couldn't use the digits more than once. Let's look at permutations with restriction. So how many numbers are there that can be made out of the digits 0 through to 7, such that all the digits are used once and once only? The length of the number must be 8 digits, and if the numbers are to be divisible by 5. Note that numbers starting with 0 are not allowed. Well, for the number to be divisible by 5, the last digit, the 8th digit, must therefore be a 0 or a 5. Let's look at this in terms of slots, like we did with previous examples. So there we have a choice of 7 digits for the first 7 slots, because we've already chosen 0 to be in the last slot. The other alternative is choosing 5 for the last slot, and then because we can't use 0 for the first digit, we have to consider that separately to the other middle 6. So in this case we would have 7 factorial choices times really no choice or 1 choice there. Whereas here we have 6 choices for that first slot because we can't use 0 and we've already used 5. 6 factorial for the middle 6, and then that was a choice there. So here we have it written out a little more neatly with the actual figures for 5040 and the 4320 permutations. You can see the use of permutations here, and I really would not have wanted to list all those numbers. In total then that gives 9360. Here is an example for you to try. You may wish to pause to do this if you would like to do it but need a hint. Firstly, think of the digits that you would choose for the number to be odd. Secondly, think about the fact that the number 2 is repeated. So here we have the fact that that last digit had to be either a 1, a 3 or a 5 for the number to be odd. Therefore there were 3 choices. You then had 6 numbers into 6 slots would have been the 6 factorial, but because you have 3 2's, you had to divide by 3 factorial to adjust for the repetition so that you got different odd numbers. All in all then, 360 different odd numbers would have been possible. In the next session 1.5, we will be looking at combinations.